Thanks everyone for coming. It's a pleasure to give the second talk. Let me just jump into it. So throughout we fix G will be a split reductive group over the integers. And last time we associated to it the Hyodo-Kato, so the algebraic version of it. So it's the double quotient of the loop group by the positive loop group. And it parameterizes modifications of G bundles on the disk. It's a Hyodo-Kato. And what I talk about today is the following theorem.
So what topology can you remind one on the test category and the topology?
Sorry, can you repeat?
So when you have a stack, you have a category and you have a topology. So the category like schemes over Z and the topology is FPQC or FQT.
Oh yes, so the test category, just say the test category of rings. Yes. And the topology here is the étale topology. Yeah. Okay. So a priori you would think that maybe you should take a bigger topology because this positive loop group is, I mean, it's not an étale group scheme, but that will suffice for the purposes. In fact, you can show that this is already an FPQC sheaf. So the étale sheafification. The theorem is, so there exists a symmetric monoidal equivalence. So the category on the one side is the category that was introduced in the first talk. It's the perverse state motifs on the Hyodo-Kato. And what appears on the dual side, or on the other side, are representations of the dual group, but now in which category? Namely here the base category is state motifs on the spectrum of the integers. So here these are representations of this guy internal to that category. And can also, so we also had the intersection complexes, and we work with rational coefficients in the cohomology theory, and they go to the highest weight representations, and there's the same twist appearing.
What is the T? Can you, inside ref, what is written?
Tate motifs on the spectrum of the integers. That's the heart of the category of, so you have inside all motifs on the spectrum of the integers, you have the full subcategory generated by Tate motifs, and this has a T structure.
So which kind of motifs? Do you use the étale motifs that were discussed before?
Yes, I do the étale motifs. It's not the rigid. I'm back in the algebraic world.
Étale motif, the coefficient ring is
the rational numbers for simplicity. You can let me say something. So the version as it is, this appeared in joint work with Schollbach, and this is with rational coefficients. And there is also a variant for the width vector Hyodo-Kato. So then there is subsequent work of Kass, Van den Hofe, and Schollbach. So they also have a integral, so a version with integral coefficients. So the proof I want to discuss today of this, it goes along the lines of their proof with integral coefficients, but with rational coefficients there are some simplifications. So Oops.
Yeah, let's ask, just remind me, do the data depending on mu, do they only depend on the biolobbit of mu, or did we choose a kind of Borel secretly somewhere?
No, it's canonics. It's what I'm trying to explain today.
So, but the V mu sort of a priori, I guess that depends on the biolobbit of mu, right?
The mu depends on the biolobbit of mu, yeah.
Also, will you say something about how the left-hand side is a symmetric monoidal category?
Unfortunately not, this I swept under the rug. But maybe let me say a little bit right now. There are two ways I know. I mean, there is work of Guglielmo Nocera, so he manages to put at the derived level, equip this category with the E3 structure, and then the heart will be symmetric monoidal. But the more classical way, let's say, doing this is just equip the heart with a symmetric monoidal structure.
So some sort of convolution on this space?
Right, for the convolution.
Bayesian-Drinfeld-Grassmannian?
Yes, and for this there are also two ways. So there's one via the Bayesian-Drinfeld-Grassmannian, which is kind of rather global argument, and there is a purely local argument due to Chin-Wen-Ju, but it's combinatorial quite tricky.
The symmetric monoidal structure you get from fusion isn't the one that gives this equivalence, right?
You have to modify the sign. Yeah. That's true, thanks.
There's an issue with the commutativity constraint because the fiber functor has Z grade.
Okay, so and there's another one of this equivalence. So due to Scholz, he works with the BD-Rham plus version of the Heckestake and the 1/p coefficients. Okay, but let me maybe jump back. What I start with today is a reminder on the classical Satake isomorphism. There you can also see some of the structures that we have there appearing. And here the basic definition is, or the basic object of study is the spherical Hecke ring. And my notation for this is like this: H, G, and Q. And what you look at is at finitely supported functions on the QP points of the Heckestake, and with values in the integers, let's say. In representation theory, you often look at this ring with values in the complex numbers, but let's just do the integers. We can tensor up if you like. And then the second basic definition is there is this extended version of the dual group, which plays a role in defining the C group. So you look at the semi-direct product of the dual group with GM, and here GM acts via the adjoint of rho. So here rho is the half sum of the positive roots in G, and we regard this as a character towards doesn't land in the dual group, but in the adjoint of the dual group. And then you can act on the dual group by conjugation. And this guy here, it comes with a map to GM, and let me just denote this map by D.
So the FQ points, you mean FQ points up to isomorphism in the definition?
Yes, that's what I mean. Yeah, isomorphism classes of. And it's really the étale. You can show that the étale topology doesn't play a role here. It's really the G. So F value points of the group G modulo the O value points of the group G, where F is a local function field and O its string of integers.
And it injects to FQ bar points. The FQ points inject into FQ bar points?
Yes. Yeah. Okay, just following a theorem. Of course this has a long history, but this version I'm stating is in a paper of Zhu, and it's the version of the Satake isomorphism referred to in this paragraph here. And let me state it in a slightly sloppy form, namely saying there is, should do 1 over Q, there exists the adjoint 1 over Q algebra isomorphism between what? So on the one hand, we have the sec algebra, but then we invert Q. And on the other hand, we look at this extended dual group and restrict to the fiber at D equal to Q. So, and take the, conjugation invariant functions under G check. So that's a variety with an action of that group. Okay, so how does this relate to maybe the more familiar version? So it's following remark. One. So the choice of some square root of Q, this induces an isomorphism. So as G check varieties between this fiber here and just the dual group. Okay, so then you get back to the more familiar version of this Satake isomorphism, and namely, let's think about from another perspective. This isomorphism here depends on the depends on Q. So what in this motivic thing, what we are doing is we are somehow, it's a parametrized version of this isomorphism where we are also varying the Q. Hence you would like to parametrize some version of the isomorphism where the isomorphism itself does not depend on the choice of that Q. So, for example, doing this here does not behave well in families.
Sorry, what's the gamma Q here?
Square root of Q.
Oh, square root of Q.
Right.
Yeah.
So Q is a
Q is a number.
Any number?
It's a prime power.
Prime power.
So you can form a finite field.
Okay, so
yeah.
prime power.
Prime power. Yeah. No, there are also versions where Q is like a formal parameter, and but it's not that. Okay. Okay, then you can ask, okay, cool. Now, you have this version. Can we do better and not invert the Q? And yes, you can do. Namely, we have that D here, and now let's think about it. Once we have to restrict to the fiber over Q, since this lands in GM, this forces the Q to be invertible. Okay, so if you don't want the Q to be invertible, you have to complete this, and what appears here is some monoid completion of this group. It's just a monoid. VG rho. I don't explain the construction here, but construction uses some Tanakian formalism, and it's constructed from the so-called Windberg monoid. And then in this case, it's also the version due to Zhu, you get an isomorphism of the full Hecke algebra with integer coefficients, and then you restrict to the fiber over Q of that monoid. So like so. And I would like to take some time and explain this in the example of PGL2, because I think it's nice. So how does this work in the PGL2 example? So in this case, this group here, so the dual group is SL2, and this group is just GL2, and the D is the determinant. So down to GM. And then in this case, so instead of looking at a few points of the Hecke stack, you can look at the like L plus G orbits of the FQ points in the Afan-Grassmannian. And this here, I guess is Breuer-Titz. Then these are the vertices of a Q plus one regular tree. In other words, these are just like homothetic classes of two-dimensional lattices. And let me also draw a picture for Q equal to 2. So just it's like this, and then it goes off to infinity. And in this picture, the Hecke mu of FQ. So mu, these are the dominant co-characters. In this case, this is just the non-negative integers. And here, in this picture, this just corresponds to the vertices x with fixed distance equal to mu from the origin. So here's E. And in these terms, we can just write down a basis for this integral for this spherical Hecke ring. This has a Z basis given by the T mu's. So you sum over all vertices x with fixed distance mu, and then delta x, this is the indicator function on the vertex. And mu is just a non-negative integer. And what is the ring structure? Namely, to explain how to multiply such guys, it's enough to explain how to multiply this with another indicator function. So this will be, you just sum over the vertices of distance mu, but now from y. So we'll over those x such that the distance x mu is equal to y. Okay.
I'm sorry, I'm a little bit confused. I thought that the vertices with distance mu are points of the Schubert cell. At like a mu, we have to further quotient out by G of O, no?
Right, you kind of take the inverse image. Yeah, maybe I should write.
So are these vertices with fixed distance form like the orbit under?
Yes, they they form an orbit under the positive loop group. Okay, cool. So, and now what is the lemma here in this case? The claim is, in this case, so the map given by, so it turns out that you have to modify the spaces slightly if you want on the dual side see something, see representations appear. So with mu congruent to lambda modulo 2. So you, namely, for example, if you read in Serre's book about trees, there already appears this distinction between some vertices of odd distance and even distance from the origin, and this is also what you see here. And this you map to, on the other side you have a representation ring, and the brackets denote the trace of this representation. And it's just the mu's symmetric power of the standard representation. And the claim is that doing this induces isomorphisms maybe, between on the one hand, so let me write here the things with Q inverted. Determinant equal to Q. And inside there, PGL, the integral algebras. Particular, this Hecke ring is torsion free, so it's really a sub. And here you get, well, what is the monad completion? In this case, it's just 2x2 matrices. So restricted to determinant equal to Q. And then SL2 inside here. Okay. And the proof is also not difficult. I mean, basically, maybe you have to know a bit about these rings, but basically you observe that both these guys, they are Z bases of these rings. And the only thing you have to check is that this is a ring map, actually. And to check that this is a ring map.
What are your matrices what are the coefficients of your matrices?
It's the matrices over the integers as a monad. Is over the integers as well. But then you invert the Q.
So Q is a formal parameter or
no, Q is Q. I mean, it's a prime power, yeah.
So it's a prime power not equal to 1, p to the 0.
Oh, yeah. It's not necessarily power.
So, but this notation with the Z1 over Q and then brackets, something that stands for like the affine coordinate ring. Is that right? That variety? Just.
Oh, yeah. In brackets is the affine coordinate ring, yes. Oh, by the trace.
Trace of the representation.
That's these brackets. I didn't want to calculate with the trace. So. Okay, but what the basic computation you have to do, you have to see that both bases multiply in the same way. And what you check is that if you multiply this, you get IC mu plus 1 plus Q times IC mu minus 1. this is also, if you think about the difference between this T basis and this is what is called the Kashdan-Lustig basis, they basically have the same multiplication rules, except if you multiply T1 with T1, so multiply T1 with T1, so you have to sum up over the vertices of distance 1. You have to sum up all points of distance 1. You will sum up the base point one time too much. And this is then by a recursive formula where it's suggested that you do this. And here, what is it on the other side? It's like, if you like, first symmetric power, tensor the mu symmetric power. It's the mu plus 1 symmetric power plus. And then you have here the determinant times the mu minus 1 symmetric power. Like this. And then you see if you plug the determinant equal to Q, then it fits.
And this isomorphism is over Q or over Z? Which one? So this is a ring. This is not a Q algebra. This is just a Z algebra. Oh, over Z. Yeah.
And is this 2x2 matrices just the Wimberg monoid in this special case?
Yes, it is. Yeah. It's the Wimberg monoid in this special case. It's a bit unfortunate. I mean, some of the construction of this is quite inexplicit, and it's pretty hard to work out what this is in other cases. Okay, so here you already get a hint on what to expect from this geometric thing, and what I want to talk about in the second half is a proof of this motivic Satake. And I would like to start with so-called constant term functors.
Timo, could I just ask, so you had a theorem about your motivic Satake.
Yeah.
And you had a discussion about the Satake isomorphism.
Yeah.
And what's the connection between the two?
Ah, this I want to say in the very end.
Okay.
Okay, so it's about constant term functors. And here, let me fix split maximal torus in a Borel in G. And you look at the following correspondence, namely on the level of affine Grassmannians first. Like so. Then here, this affine Grassmannian maps to the Hecke-stack of G. And this here maps to the Hecke-stack of T. And you want to use this correspondence in order to get a functor from motives on the Hecke-stack of G to motives on the Hecke-stack of T. And only has to be a little careful what to write down. Namely, you take this diagram here and mod out everywhere by L plus T. So you still have these maps. So this here is just the definition. And let me denote this by notation P. Oh no, P and Q are already gone. Pi, yeah. Pi and phi, I don't know. Ah, no. Okay, pi and phi. And then the following definition, namely this constant term functor, it's the pull push for that diagram, but there's a little shift involved. So pi upper shriek, phi lower star, and so I explain in a moment what this degree shift is. So it goes from motives on the Hecke stack by definition to motives on the Hecke stack of T.
Just to check, this is a kind of geometrization of the Satake transform.
Yes, it is. Yeah, also in the Satake transform you see that shift appear.
Does that mean you have to check some convergence, kind of convergence?
No, here you do have, yeah, no, somehow. I mean, already this algebra you don't have a Haar measure or something, right? It's just combinatorial, and so implicitly what is happening is that you give L plus G volume 1 somehow.
But you don't have to worry about it. Like in the Satake transform, there's kind of you have to check the integrals kind of make sense because you're integrating over something non-compact.
Oh, yeah, right, yes, that's a good point. This, we build it into the formalism of the sheaf theory somehow, making sure that these functors exist, right?
Yeah, okay.
Yeah. Yeah. Here, this degree, it's a locally constant function on the Hecke stack of T. So you go to the connected components. These identify with the co-characters, and then you pair with 2 row and get an integer. So this is a locally constant function, and we can do a cohomological shift by negative of it. And maybe just to comment this, that here the negative arises that really somehow you could also do star push forward and shriek pull back, but only that our sheaf theory does not have these operations in general. Huh? Yeah, that's why I explained a lot about the extension of these things to arbitrary pre-stacks, maybe with some conditions. You can now just use that formalism to write down the functors you would like. So the theorem here from appears in work of Karls van den Hofer and Schollbach. So I said it in the beginning, but say it again. So the proof strategy I'm explaining is the one that is also in their work on the integral story. Namely, this constant term functor satisfies the following properties. There's one. It's conservative. 2. So reflects isomorphisms, or you can detect when an object is 0. It also preserves and detects stratified Tate motifs. And 3, It also preserves and detects porous stratified Tate motifs. Perverse. Okay, namely, just by comparing with the story for other cohomology theories, maybe 1 and 3 are known in other cohomology theories as well, but somehow the heart of, I mean, just in comparison to existing proofs, the heart is really that it preserves these stratified Tate motifs. And let me comment on this. So that's the preservation of stratified Tate motifs. And there's a geometric reason for this. Namely, if you think about what part of the geometry here in this correspondence plays a role, you run into what is called the Merkovich-Villon cycles, and namely for any dominant co-character and for any co-character. These parameterize the orbits on the Hecke stack for G and those on the Hecke stack for T. You have, I can call this variety X. You take the mu orbit in the affine Grassmannian and intersect it somehow with the thing you have in the Grassmannian for the Borel. So nu is a point in here, and you take the pre-image and you get a component in here, which maps in a as a locally closed immersion into the affine Grassmannian. And you take this, and this is a locally closed subvariety in that mu orbit here. And this is what's called a Merkovich-Villon cycle. And the key claim is that this admits a filtration by closed subspaces like this. So x goes to x0.
And these Merkovich-Villon cycles work in this case of SL2?
They are, in the case of SL2, I mean, in general, the irreducible components are the weight spaces you see. And in the case of SL2, you have multiplicity 1. So in this case, it's either just affine space, or it can sometimes happen that you also have a product with a GM. And the claim is that this happens always in the following sense. Namely, there is such a decomposition such that the if you take the complements, this is isomorphic to some power of the affine line, or some power of this here for some AI, BI, non-negative integers. And this is really what then allows you to see that if you do this push forward along this direction, that this preserves state motifs. So,
what did you say about the relation with weight spaces in the representation?
Oh, under geometric Sataki, the number of so this is equidimensional of a certain dimension, and the number of irreducible components they correspond to the new weight space in the highest weight mu representation. let me would like to stress, I mean, this relies on earlier work of Gosson-Littelmann over the complex numbers, and is implicitly contained in there. But this is, I mean, to construct such a decomposition is combinatorially really involved, so it's not easy.
So here your GRG mu is it the double coset, or is it like closure of the double coset?
It's the L plus G orbit of mu in the affine Grassmannian. So okay, so these constant term functors is like one ingredient. Another ingredient is, so it's supposed to be some kind of Tanakian equivalence. There's supposed to be a fiber functor. And here, let's look again at the map from the affine Grassmannian and then towards spectrum of the integers. So F and G maybe.
So this X is reduced as a scheme?
I'm not 100% sure.
Okay, but then you can take first X reduce and then the complement is M.
Right.
Okay.
I have to think about it. At the moment, I'm not 100% sure. So this fiber functor takes values in Tate motifs on the base, and what you do is you take an object and you sum over the cohomologies computed internally, so like the sheaf cohomology. Namely, you first take your object here, you pull it back to the affine Grassmannian, and then you push it down to the base. And then you sum up over the cohomologies and you land in here. And this is also precisely, this sum here causes causes a sign issue with the fusion product. It's simply because tensor products of complexes, if you switch it, you have a sign. And the reason it works here is that on each connected component, an object is either completely concentrated in even degrees or completely concentrated in odd degrees. This is what allows you to fix that. And also, let me here be very brief. What you can show is that this functor, this upgrades to a symmetric monoidal equivalence. From where to where? So parasite motives on the second stack to and then co-modules under some Hopf algebra. Let me write this as OG tilde internal to Tate motives on the base. Okay. And here, so some proposition. So, namely, a priori it could be that there is some, I don't know, subtle interaction between this Hopf algebra here and the structure of that category. but the thing is there is not. So, and the way to say it is that this OG tilde that lies in the full subcategory which is just, in this case, Z-graded Q-vector spaces. And, oops, let me make some, no. Maybe let me write it on the board here. Here, this, oops. So this sense we twisted I, this is my notation for we in degree negative I, unfortunately. Well, it's like this. This goes to V tensor with the I state twist.
Sorry, I think I just missed. What was G tilde?
Oh, it's some Hopf algebra in that category.
So G tilde just means.
Right. It's just a notation for. It's a Babek style of argument where you get an equivalence between this and co-modules here, and then this is a priori only a co-algebra, but then you have to do a bit more work, and you see it also has an algebra structure which matches the convolution structure here. Right. Right. It's a Tanakian thing in steps, and then you want to say somehow what that G tilde is here. Let me change the boards. Oh. And what you conclude from this is that G tilde is at least some affine Q group scheme, together with a Z grading of its global sections. And such a Z grading is equivalent to GM action on that G tilde. So somehow this extra GM comes from the presence of the Tate twists here. And let me briefly indicate how this works in example. So G is again PGL2. And you have phi is the minuscule guy. Then this Schubert variety in the affine-Grassmannian is just a projective line. And this intersection complex is just a constant sheaf on the orbit, shifted by 1. And in this case, what the geometric Satake is claiming is that this here is isomorphic to the special linear automorphisms on what? On the cohomology of that object. Here. And maybe let me write it again here. What is this cohomology? it's canonically Q, and then Q in degree -1. And this is just SL2, but now it has a GM action, and this GM action, this here is somehow via and now the normalization with the grading. So here you have weight 1, and here you have weight -1. So A lambda B lambda inverse C D.
Sorry, so Timo, here you're picking up the GM action because of keeping track of Tate twists.
Yes.
But could one also get the same thing just by keeping track of cohomological degrees?
Oh, yes, I think so. Okay. Yeah. Yeah.
So even in the Betty theory, kind of one could
I would think so, yeah. Okay. And let me do a slight warning. Here it really let's say we're in a classical setting where we are an over algebraically closed field, and maybe we have some L not dividing K. Then it's true, of course, that the second analytic cohomology of P1 over K, this is isomorphic to QL, but this isomorphism depends on the choice of a compatible system of L to the nth roots of unity. So. And even in the Betty setting, you would still have to choose plus or minus I. To talk about the identification of that G tilde, and for this it's useful to fix some auxiliary T and B and G and a pinning. And then in the last step, one would show that what we did does not depend on that choice. So this is pair state motives on the Hecke stack and the constant term functor towards the Hecke stack for the torus. Yes, so this, let me, thanks. Like so. And this is representations of some T tilde. And proposition. This constant term is also equipped with some symmetric monoidal structure. The structure. And also with isomorphism of functors, where you first go through the constant term and then postcompose with the cohomology on the torus. Okay. What this gives you is that you get a map from T tilde to G tilde, and then there's some extra arguments. So basically, up to retracts, the essential image generates this category here, and so this here will then be a closed immersion. And you also have a Borel subgroup, so tilde and G tilde. That's a subgroup stabilizing the following ascending filtration. I less or equal to n, h, I on G on the cohomology functor. Oops. So this gives you is T tilde and B tilde and G tilde. This one here is it's easy to see. This is canonically the dual torus, and it's a split. In fact, a split maximal torus in here. This here is reductive over Q. For this under the Tannakian formalism can be read off in terms of properties of the category, and this here will be a Borel subgroup. And then I guess theorem is there exists a pinned isomorphism towards the dual group with its canonical pinning, so identifying these groups, so inducing T tilde equals T check, P tilde equal B check, and also the Z grading agrees with GM acting via the adjoint here at rho. So I won't have time to comment on this, but if you're interested in how things fit together, just come and ask me. So instead, in the last minute, let me connect this picture to the classical Satake isomorphism. So let me write one diagram and then stop. Namely, to connect it back to the classical Satake isomorphism, we base change the hackestack to the finite field FQ. And then we have this equivalence to representations of the dual group on Tate motifs of FQ. And this here is just the category of Z-graded vector spaces. And so this here is the same as representations of this Deligne modification of the dual group. And also inside here, you can sort out a smaller subcategory which is stable under convolution. And that's a subcategory where you only allow negative Tate twists. So let me call this anti-effective or so.
Sorry, so now you're using the integral version of the Satake to base change to FQ, not the Q linear?
Oh, the hackestack the whole time lives over spec Z. So the integral version refers to a version where the affine Grassmannian lives over spec Z and the coefficients are also Z. So now here's everything with rational coefficients. And under this, this thing will map to the representations of that Winberg monoid. Okay, let me stop here. Thanks.
So I have two questions. One probably just yes or no. Like, so you kind of base change everything to FQ, and I guess everything is somehow that's compatible with that base change.
Yes.
Yeah. But the other question is, how do these arguments kind of compare to, I don't know, like Merkovich and Villeneuve's argument, or just other traditional proofs?
Yeah, sorry, I wanted to say this. I think the similar is so the strategy is very similar to Merkovich-Villon's classical argument. There are then some tweaks in Fark-Scholz's proof and some further tweaks in that integral motivic version. Yeah.
So in this theorem of Cass, von Schollbar with integral coefficients, it's still the pure group which appears, I guess, but they don't restrict to this anti-effective.
No, it's always the dual group that appears in some sense, right?
Right, but on the other side, they don't put this anti-effective restriction.
There's one chapter where they explain this anti-effective thing.
What is anti-effective here?
You only allow negative Tate twists.
Okay. And what is the right-hand side representation of
this Winberg monoid thingy? Q vector spaces.
Okay, you don't have finite dimensionality? Okay, because you don't have...
Right, but there is a version of this where you can write here abelian groups instead.
Can I just check my understanding? So when you stated your motivic Satake theorem, your hackestacks were over spec Z.
Yes.
Now when you're applying it, you apply it where your hackestacks are over FQ.
Yes.
But one doesn't follow formally from the other, right? You kind of just have to give the same argument in both settings, or?
Yes, I should have fixed the base and then work with that base.
I see. Okay.
Yeah.
Why do you use the constant functor for constant functor in the conservative or stratified module?
Where it's used exactly? Well, I mean, what I swept under the rug, at an early stage you already prove the compatibility with the constant term functor and the fiber functor. And then you deduce properties of the fiber functor from properties of the constant term functor. In particular, you want that the fiber functor is conservative as well, in order to apply this Babek kind of argument. So it was somehow implicitly used in the conservativity of the fiber functor and then this Babek argument. Babek?
Babek, he said.
Babek theorem.
Okay.
Thank you again.